Well, good afternoon. Thank you for coming for this nice colloquium. It's for me a great honor and pleasure to introduce today one of the best scientists, best particle physicists that I know, one of the most humble persons as well. And for me, a scientist who beyond research does a great contribution to humanity to prepare ourselves for the future through education today. So let me just say a few words, invest some time to enumerate some of her achievements. So Professor Helen Quinn was born in Melbourne, Australia. She obtained her PhD at the University of Stanford in 1967 under the guidance of James Bjorken. I guess that most of the students here know him well. At that time, only about 2% of the physicists were women, so you can imagine what was going on in those days. Professor Quinn then did a postdoc at SLAC and then continued at DAISY before being appointed as assistant professor at Harvard University. I guess now I got it right.
You did.
Yeah, very good. She then moved back to the Stanford Linear Accelerator Center, SLAC, where she became staff in 1979 and professor in 2003. Her more than hundreds of papers, 190 about, include 85 with original research, and have been cited really like an absurd number of times. Probably her greatest contribution has been her proposal, which she made together with Roberto Peccei, of the so-called Peccei-Quinn theory, which explains the source of violation of CP in strong interactions, the absence of the electric dipole moment of the neutron, and in more recent extensions, even a possible nature of dark matter and dark energy by the introduction of new particles. But since this is the topic of today's colloquium, let her teach me exactly what that all means and how this was developed. She has also pioneered the research on grand unified theories in hadron physics and has pointed out recently different aspects of the so-called baryon asymmetry of the universe that might be useful today in today's research. All her life, but especially since 2010 as Professor Emerita, she has led great efforts on science education projects, including multi-state education policies in the US and the establishment of the new National Education University in Ecuador. And I have heard yesterday, actually in the night, that she is involved in some efforts to include science as an important element in the Mexican public education system. Thank you for that, because we need it. For her scientific work, she has received, among many other distinctions, several awards worldwide, which include the Dirac Medal 2000 from the ICTP, the Oscar Klein Medal 2008 from the Royal Swedish Academy of Sciences. I must mention here that she was the first woman to get it. So congratulations as well for that. The J.J. Sakurai Medal for Particle Physics 2013 from the American Physical Society. And well, among many others, also the Benjamin Franklin Medal in Physics 2018 from the Franklin Institute for her great contributions on grand unified theories as well. Today, in the context of the 18th anniversary of the Institute of Physics of the UNAM, she accepted to share with us her time and her knowledge in a colloquium on that theory that she developed. And I thank her, and I guess we all thank her very much for her time and her possibility, her acceptance to come and visit us. Thank you, Helen. Welcome.
Thank you. Thank you very much for the invitation, for the nice introduction. And I'm going to talk about the development of the idea, but I am not going to explain the idea. Because in this colloquium at this level with this range of audience, it's too technical. And I think if you don't know what it is, you won't learn it in a colloquium. So I'm going to talk about it at the conceptual level, but not at the technical level. And that, I hope, will not disappoint the people who wanted more technical details, but those you can find in the papers. So let's see if I know how to work this. So as I said, ideas will dominate over the technicalities. Occasionally there's a technical slide. If it doesn't mean anything to you, if you can't read it, don't worry, it won't hurt. You're getting the general idea of the talk. And I apologize, my slides are so dark on this projector. I don't know if you can read the blue, but I hope you can. So Roberto Peccei was working with me at Stanford, and he was the one who asked the critical question. And of those of you who are researchers know, finding a new idea, the biggest contribution is finding the right question to be asking at the right time. And so the question was, we know that there's CP violation in the weak interactions, and we know that there's very little CP violation in the strong interactions. And in a QCD theory of the strong interactions, that's actually hard to understand, because it's easy for loop corrections for the weak interaction CP violation to break CP effectively in the strong interactions. And the fact that that effect is so small is the problem we were trying to solve. So, I mean, for background, for those of you who are not the experts, I'm going to start a little bit with what we mean by symmetries and what these discrete symmetries, when we talk about CP, what that means, and a little bit of the history of how we know about this breaking before I get to really talking about our own contribution. So those of you who are the physicists should recognize Emmy Noether, because she is the one who told us this fundamental theorem that symmetries have consequences in the physics. And in particular, continuous symmetries have consequences of conservation laws. Discrete symmetries also have consequences, just a little bit differently. So the universality of physics tells us that we should write our physics equations so they don't depend on the position coordinates or the time coordinates, because physics is the same at any place or at any time. That tells us something about how we have to write the equations, and that gives the symmetry, the equations a symmetry which is invariance under time translation and invariance under space translation. And what Emmy Noether told us is the consequence of that is energy momentum and angular momentum conservation. This seems miraculous, right? These are not things we discover phenomenologically. These are things that come out of the mathematics of making physics universal. And in fact, we really have no proof by experiment of energy conservation. We only have this. And energy conservation is one of the most fundamental principles of how we understand the world around us. This is hard to explain to children who are first meeting the concept of energy. And I think it's one of the concepts we teach very badly, in fact, because of the fact that in actual everyday processes, it doesn't appear to be conserved. Okay, going back to the CP and T, it turns out these three discrete symmetries play a fundamental role in field theory. C is the symmetry that converts every particle into its antiparticle. And if C is an exact symmetry, that gives you a relationship between rates. If two particles or antiparticles collide and produce two others, turn each particle into its antiparticle, and that process should have exactly the same rate. So that's what C symmetry means. P is a symmetry which turns every coordinate into its opposite. It's actually mirror symmetry plus a rotation. And T reverses time, or it reverses the role of the incoming states and the outgoing states. So particle A plus B goes to C plus D. The rate, if T is a symmetry, the rate for C plus D goes to A plus B should be the same. So the backwards and forwards in time. So these microscopic rate equivalences are actually not true, right? But if we take the product of all three operations, that is an exact symmetry in any field theory, or at least any field theory that has the right mathematical structure. I'll come to it in a minute. So until 1956, in fact, everybody thought all of these were exact symmetries, because when you start writing down physics theories, it's very natural to write theories that have these symmetries. In 1956, parity violation was discovered, but parity violation together with C violation, so that the product CP still seemed to be an exact symmetry. In 1964, experiments showed us that CP was not exact, and I'll show you some of the effect of that later. But if we know it's not exact, we have to write a theory where it's not exact. People did not know how to. In 1973, the first theory, modern theory that has CP violation was written down. Why? Because you actually need lots of different particle species to be able to write a field theory which has CPT symmetry, but not CP and T separately. And so at the time this is when I was a graduate student, this was one of the big puzzles of physics. CP is violated, but we cannot write theories that do that. And because it would be crazy to write theories with so many, we were just beginning to think about quarks. And we had only 3 of them. To write a theory with 6 quarks, that would have seemed a little crazy in 1964. But that's what Kobayashi and Maskawa did. And they did it in 1974, actually, when experimentally we still only knew about 3 quarks. So they were really making an extrapolation in order to get this symmetry violation into the theory. So, as I said, CPT is required, provided you have a local Lagrangian, Hermitian, and it has Lorentz invariance. Again, technical terms, but those are fundamental properties for a theory that we want to have. As I was talking about originally, the universality and the unitarity that we want to have as results of any physics theory, those are necessary, and they enforce CPT. This is not necessarily true if you go beyond field theory into string theory, but it's true in string theory. So it's still a question today, are there processes which violate CPT? But we've certainly never observed any. Can you read the blue? No. Oh, I have to read it for you then, because the blue are the emphasis points. Terrible, sorry about that. So, what are CPT, what does it mean CP is violated? What kinds of things happen if CP is violated? Well, I told you about the equality of rates when you turn the particle into the antiparticle. C and P are violated, so you actually have to turn the particle into the antiparticle and reflect the coordinates. And then the rates are equal, or close to equal, if CP is a symmetry. So if you see a difference between a rate and its CP reflected rate, that would be a violation of CP symmetry. And in fact, we have seen that. There are a particular set of particles, and I'll show you what they are in a minute. They're the neutral mesons, which are made of a quark and an antiquark of different flavors, right? And there, let's take the K meson. It's made of a strange quark and an anti-D, or a D quark and an anti-strange. So that neutral meson, actually, there's 2 different neutral mesons. And they go into one another under CP. So, actually, they go into one another with a minus sign, but that's a technical detail. So the 2 states are not eigenstates of CP. But if CP is a symmetry, it tells us that the eigenstates of mass must also be eigenstates of CP. And so they're admixtures of the flavor states, equal admixtures with a plus or a minus sign. The other thing that you have, and this comes more in the meson, you see this in the B mesons, where there are 2 states. You always produce quarks of a particular flavor. So you produce an admixture of the states of equal mass. And then you have all kinds of interesting quantum mechanics as they travel and mix, so you can produce things with one flavor and have it decay with a signature of the opposite flavor. Or you can produce it with one flavor and have it decay to a state that either flavor can decay to. So you can know what's going on, and you can look for an inequality between the decay rates of a B to a particular final state before it's become an anti-B or after it's become an anti-B. And those 2 decay rates should be the same if CP were a symmetry, but they're not. So that's another form of CP violation. The other thing that would be a CP violation if we had seen it is the neutron. This blue print is about the neutron electric dipole moment. If there were CP violation in the strong interactions, that would induce an electric dipole moment for the neutron. Now, the neutron's a neutral particle, but it's made of quarks which have charges. So in principle, those quarks could have distributions that give you a dipole moment for the neutron. However, CP says that and the reflected state should be the same, and so the neutron should not have a dipole moment. And in fact, when we try to detect the dipole moment, there's a very, very small upper limit. Of course, you can never say experimentally that something is absolutely zero, or rarely, but you can say it's tiny. And that can put a limit on the CP violation in the strong interaction processes, which is tiny. And that is the puzzle we're trying to solve. Okay. Here we talk about the mesons. For those who couldn't follow me in words, maybe you can follow me in writing. All these neutral mesons are made of different flavors of quarks. Strange and down, up and charm, B and D, or B and strange. And there's always one quark and one antiquark for each meson. And for the K mesons, here's exactly the states written down. And so when I first wrote it, I had the signs wrong because the CP takes a K into a minus K. So actually the state with the minus sign is the state that goes into itself with a plus sign under CP. And the state with the plus sign goes into minus itself under CP. Because, of course, the K0 goes into the anti-K0 under CP. Or rather, it goes into minus the anti-K0. So this is the mesons that have all kinds of interesting experimental consequences on CP. And the 1964 discovery was you took, another fact about these mesons. A K meson can decay into two pions. But if we make a neutral kaon decay into a pi plus and a pi minus, and the neutral kaon has spin 0, so it's a pi plus and a pi minus in a spin 0 state, that state is CP even. So CP symmetry would say that the CP even state can decay into pi plus, pi minus, but the CP odd state can't. So it can only decay into 3 or more pions. And it turns out the mass of the K is not much bigger than the mass of 3 pions. So the decay to 3 pions has a much longer half-life than the decay to 2 pions. So these things are also called K long and K short. But it turns out K long is not quite the CP odd, it's the odd state plus a tiny bit of the even state. There's a small admixture, which means CP violation is there, but it's small. And this is what was found. That was the puzzle in 1964, which is solved by the Kobayashi-Maskawa theory of 3 generations. And the problem, why do we need 3 generations? The reason is all of these effects of CP violation I'm talking about are interference effects. You have to have 2 states with 2 different couplings that interfere, two processes with 2 different couplings. They'd interfere with one another, and then you can get rate differences between the sum of them and the sum of them for the CP conjugates, where all you do is change some phases. But phases can be removed in the Lagrangian by making redefinitions of the fields. If you have a coupling constant times a product of fields, then you can change the phase of the coupling constant by, so here's an example. Here's a term which would be the coupling of the W boson to a quark and an antiquark, right? And it has a certain coupling strength. Now let's suppose I redefine the quark field by just changing its phase. Well, I can rewrite the Lagrangian. It looks just the same for the new quark field, except the coupling constant has a different phase. Okay, so if I have a complex coupling constant, I can make it real by playing this game. And I can do that 1 quark at a time until I run out of quarks, right? It turns out if you have the standard model with only 2 generations of quarks, you can remove every phase by this trick. And so there are no interference terms. So there is no CP violation. And you have to have enough different kinds of particles that, and it turns out, the other question, if you think about it, let's say you have quark-quark Higgs field. the more different kinds of quarks you have, the number of couplings grows faster than the number of quarks, because each two types of quarks can couple to the Higgs field. So if you have 3 generations, it finishes up that this matrix, so these are all the different couplings of the W boson, and after I've gotten rid of every phase I can, there's one complex number left. So this is the term that gives you CP violation in the standard model. Convention, of course, by convention I can move it around, but it appears here, and by unitarity also here. So these things, rho and eta, are the things we need to measure to look at CP violation in the weak theory. And I cannot resist showing this slide, because B-physics took us from 1995 to 2015, and this is, so the plot, the little triangle in the middle of this plot, this axis is rho, and this axis is eta. So if eta is non-zero, there's CP violation. Every different color represents a different measurement. So if you make lots of different measurements and fit them to a theory with only these 2 parameters, that's very constraining. In 1995, the green band that kind of swerves around and goes up there, and it's also down here, that's the 1964 measurement. That's the difference in the K states from the CP eigenstates. And it's pretty uncertain whether yes, it's clear that it has CP violation and it tells you what eta is, but it doesn't tell you very well, because the apex of the triangle could be anywhere in that green band. And the big yellow band is the difference in masses between the quarks that you extract from these mass differences of the neutral mesons. And again, there's big uncertainties. As we start doing B-physics experiments, we narrow down those uncertainties over the years till today it looks like this. So this is the asymmetry in the decays of B to J psi, K short, and it's become a very narrow band, and you put it on top of the brown band has now collapsed into the big brown band actually has a little yellow shadow on it. Now the brown is collapsed and the yellow is bigger than it. And you see the apex of the triangle is here, and it fits with like 6 different measurements, giving us the same apex to the triangle. That means the standard model has fit many, many experiments with one parameter. And it's a parameter that definitely shows CP violation. So we know this part of the standard model very well now. And we can calculate what impact it might have on the strong interactions. And you would think, so first of all, it tells us we can't say we'll impose CP as a symmetry, and that explains why CP is small, not violated in the strong interactions, because, as I said, it can affect. And it induces this parameter, and here, okay, sorry. The parameter is, there's an I here, theta, and then it's FF dual. So F alpha beta, F mu nu, F alpha beta with a totally antisymmetric tensor here. If you tried to write that in QED, it would vanish, because you're trying to antisymmetrize something which only has 2 different parameters. But because of color parameters, in addition, this quantity is not 0 in QCD and can induce CP violation in QCD. And the smallness of the electric dipole moment tells us this parameter theta is less than 10 to the minus 10. And that's the puzzle we're trying to explain with Peccei-Quinn symmetry. So here we are. We can't just set theta to 0, because that would be trying to impose a symmetry. So why is it small? Well, we knew one thing. We knew that if any quark had 0 mass, there's another kind of quark field rotations, a chiral rotation. Before we were rotating the field by an e to the I phi, it's e to the I phi times gamma 5. When we do this, we actually, because the Jacobian of the change of variables affects FF dual, we're actually changing, we can change theta. So if a quark has 0 mass, we can rotate this parameter away without affecting anything else, and we can get rid of theta. So if any quark has 0 mass, there's no problem. But unfortunately, none of the quarks do have 0 mass. So that's not the answer. But we also knew in cosmology, in the very early universe, the Higgs field vacuum expectation value is 0, and all the quarks have 0 mass. So in the very early universe, we thought, okay, we can just make theta equal to 0 because the quarks are all massless, and we fixed the problem in the early universe, and it's gone. So this is where we were. This is our mistake. We can just set it to 0, and then when the quarks get their masses, we don't have to worry about it. So it has no physical consequences. And Roberto and I actually wrote a draft of this paper. And then we went to talk to Steve Weinberg. We actually didn't tell him our idea. We just started to talk. And Steve said, wait a minute, you need to understand about CP violation. And he started telling us about rephasing the fields and changing the couplings. And he mentioned that the Higgs coupling constants, of course, would then be changed, their phases, as you rotate away the theta parameter. So you start with an arbitrary theta parameter, you rotate it away, you get complex couplings in the Higgs-Yukawa couplings. And those Higgs-Yukawa couplings eventually will manifest themselves as complex masses when the vacuum expectation value appears. And then you have to rotate those you have to make the same kind of chiral rotation to make the masses real, because of course you don't want complex masses, and you get back the theta parameter. So our trick didn't work. And as soon as Steve had talked about the Yukawa couplings, I realized, Roberto, we better stop talking and get out of here. And we did. Somehow I got Roberto to leave the room without telling Steve that we had a crazy idea that was clearly wrong, and we left the room. But this tells us what we had to think about. It said, okay, and really it's cosmology that got us to this idea, right? If we have this hot early universe, and we have it with whatever set of theta parameters and Yukawa couplings happens to be there in the hot early universe, as the universe cools, a vacuum expectation value for the Higgs field will appear. Can I make the Higgs potential such that when the quarks get their masses, it all works out so that when I make all the masses real, the theta parameter is gone? Well, clearly that means I have to design a Higgs potential such that it's theta dependent in such a way that the minimum is where the vacuum expectation value will correct for all the phases. It'll have some phase that makes everything work out so that all the masses are real and the theta parameter is 0. How can you put such a symmetry? How can you do that? How can you make the Higgs? So to be sensitive to the theta parameter means there has to be a flat direction when we're ignoring the theta parameter. And so I have to make, and then we know, we can add a symmetry, which makes a degree of freedom, which is energy independent in the Higgs potential, such that there's no theta dependence until the gauge fields get their vacuum expectation values. And the gauge condensate puts a theta-dependent term in the Higgs potential, which just makes that flat direction a little bit tilted and makes the natural value for the theta parameter to be 0. So this thinking through the story, starting with the wrong idea and recognizing what was wrong about it, was what led us to the right idea, which is add this symmetry. Now, to add that symmetry, you can't do it with just the standard model particles. You have to add another doublet of Higgs fields. And so we did that, and we wrote a theory, and we said it had all the nice properties we wanted. The minimum is dependent on theta, that's what the blue says here, in such a way that everything turns out the way you want it to. And we knew that this very simple model was rather restrictive and probably would not survive, but that the idea was general and more complex versions of it could survive. So we wrote our paper, and we didn't investigate the phenomenology of our model simply because we really expected it would not last very long. It naturally arrives, but what we forgot was that this was not a consequence of our model, this flat direction being slightly tilted. That was a consequence of our symmetry. No matter what version of the model you write with that symmetry, there's going to be one prediction of all those theories, and that is a very light pseudoscalar particle related to the degree of freedom that was flat without the theta dependence is a little tilted. It gives you the particle which is now called the axion. In other words, what this says is we add a pseudosymmetry, we get a pseudo-Goldstone boson. And that's the particle, that's the axion. So, as I said, we didn't do this. To achieve that, you had to do it. Where am I? I'm not looking. Answer yes. Okay, what this says is there are constraints on the theory from directed accelerator searches for the particles, added particles, from astrophysical consequences. For example, if you have a red giant star and you add to the theory another light and very weakly interacting particle, it's another way of taking energy out of the center of the star and cooling the star, and it changes the lifetime of the star. So you cannot ignore the lifetime of red giant stars and just add particles to the theory and not change the physics. So that's the astrophysical kind of constraint. And then cosmology, because the vacuum expectation value of the Higgs field, the additional Higgs fields give you additional vacuum expectation values. If you add too many things, you can get a theory that looks as if it works, except it gives you a vacuum value, a mass value of the condensates, which overcloses the universe, and the universe would have collapsed before now. So that's also a consequence that constrains the theory. And our original version was ruled out actually by the first two of these relatively quickly. But the more general versions with more Higgs particles, additional singlets or even additional doublets, still survive. So our second mistake was not investigating the phenomenology and talking about the axion. It took Weinberg and Wilczek separately. Each of them noticed our theory. In fact, Steve called me up and he said, Helen, did you notice that when you added your symmetry, you added a pseudo-Goldstone boson? And I thought about it for about 2 minutes and I said, well, of course we did, but I didn't notice it. And then he went, and so then Steve published a paper saying that the theory had predicted the axion. If I had said I noticed it, he would have asked me to join him on that paper. I thought that was a very decent move, so I like to tell that story. But the particle was actually noticed by Weinberg and Wilczek, that this particle was there. And it's perhaps one of the most interesting consequences of our theory, because it's a possible candidate for being dark matter. And it's one of the ways that this theory can be experimentally tested, not ruled out, but perhaps supported if we could discover that dark matter is made of axions. Now, axions have masses in the micro eV range, and light, thermally distributed micro eV particles are not cold dark matter. For those of you who don't know what that means, when you start with some fluctuation, so we start at the time the universe became transparent to light, and we know the mass density is very much more uniform than it is today, with tiny fluctuations at about a part in 10 to the sixth. And those fluctuations have to grow by gravity drawing the overdense regions and making them more overdense. And if the particles are moving at the speed of light, they escape faster than gravity pulls them together. And you don't get from the initial condition we know in the universe by reading the variations in the 2.7 degree background radiation to the universe as we see it today. So dark matter has to be something that will clump under gravity from the starting conditions. Axions are a way around that statement because they're not produced in the early universe in a thermal distribution. they're produced as a condensate. And therefore, they're not moving very fast. And they do clump under gravity. And so they're one of the few very micro EV scale particles that could be a dark matter candidate. So a very particular set of properties that comes out of this theory. And there are experimental searches going on today for these particles. These searches have just in the last couple of months published the first paper which reaches into the really interesting region in which they're given the best current theories, versions of Peccei-Quinn symmetry with axions. If the axions are the dark matter, this experiment would be sensitive to them. Here's the plot. So KSVZ and DFZV are, let's see, Dine, Fischler, Strednicki, and I'm forgetting who Z is, but two different papers, different variants of adding additional Higgs particles to our original theory. These are the allowed ranges. You'll see the mass from 0 to 2.9 micro EV. This is the interesting region in a smaller scale. And this experiment, all of this data, is this little bar here. So we're just reaching the sensitivity. We've ruled out this particular mass of axion. But the problem is to get the sensitivity, what the experiment is a cavity that's very, very finely tuned, so with a very high magnetic field in it. So if an axion goes through this high magnetic field, it deposits a little energy in the cavity. The cavity actually resonates at the right frequency, and it gives you a signal that an axion went through it. But if the axion has a different mass, the cavity doesn't resonate and you don't get enough signal. So the experiment is only sensitive to very specific ranges of axion mass. And you have to rebuild your cavity to measure the next range and the next range. There's another experiment which probably will get, and this one here, this one's at Yale, it's reaching down. This is the same kind of experiment as this one. The others are slightly different. But what the experimentalists say is over the next 5 to 10 years, they'll be able to scan this whole range with a interesting sensitivity. And if axions are the dominant particle in the dark matter, and if it's described by some theory of this type, they will be able to find them. So that would be very exciting. People have tried to find other ways of fixing this problem of the theta parameter. I still think ours is the best. I think a lot of people agree with that. Even if dark matter is not made from axions, this is still an interesting theory and is not ruled out. It just tells us that it doesn't have the right parameters to explain the dark matter as well. But it would certainly be exciting if we find that this theory also told us what the dark matter is. So I'm watching those experiments with a great deal of interest.
Why are they called axions?
Because that's what Wilczek called them. Actually, if I'd been naming them, I would have called them the Higlet. But I'm not sure that Physrev would have accepted that name. Because they're axial particles, and they're very they're an axial boson. But I don't, I know that it's a soap in this country, but I don't think Frank Wilczek knew that when he made up that name. So that's the end of my story. If you want to ask questions about any part of it, I would love to discuss it with you. And by the way, for students, if you want to ask questions in Spanish, that's fine.
Great. There's time for questions.
I should go one more slide, because I think there's a moral to this story. And that is, mistakes are part of the process of discovery. We always get it wrong before we get it right. So thinking that you have to be perfect and be right every time is just not the way to become a research physicist. You have to be ready to learn from your mistakes. And that's what I think is the moral of this story. And the second moral is experiment is much harder than theory, right? People have been searching actually for 40 years. Maybe 30 years of experiments. The first 10 years was figuring out what experiment they might be able to do that would be sensitive. And they're just reaching the interesting range now. So.
So suppose in the next generation of EDM experiments, somebody does find an EDM of the neutron. Does that rule out your theory, or is there a way to sort of stabilizing it at a small
No,
value?
it does not. There's a combination of Axion parameters that are limited, that are related to theta. I mean, it's basically how sloped is that potential. And no, finding a very small electric dipole moment would not rule this theory out.
Well, I have a question. I have two, but I will start with one. So there are some people talking right now, for example, Witten, about fuzzy dark matter with those axions that can have a mass of the order of 10 to the minus 20, 10 to the minus 23
Right.
electron volts. What can you say about them?
Not a lot, I must say. I'm no expert. But I should have said there are generations. So as you go to string theory, this idea of axions becomes almost an automatic symmetry. The extra symmetry we added is in many, many theories. Not necessarily with the parameters of the dark matter axion I'm talking about here. But so when you look at those theories, you can produce theories with axions with a great range of masses. And so people who are building theories with very much smaller axion masses then naturally ask the question, well, how could we possibly have these much smaller axion masses be dark matter? There are different classes of theories. They're just as plausible as any other theory that you can build that doesn't violate any constraints. And of course, it would be much, much harder to explore them. These tests are only sensitive to, that's why I said this class of theories would be ruled out if you didn't find the axion in this range. But other axion theories with very much lighter axions, which have this idea built in along with a lot of other ideas, such as the ones you're talking about from Witten, certainly plausible realizations of our original symmetry as well. And the term axion is generally used today for any extremely light pseudoscalar particle, whether it has to do with Peccei-Quinn symmetry or not.
I would like to ask, how is an axion distinguished from a light scalar field?
It is a light pseudoscalar field, right? When I say add Higgs doublets or add Higgs singlets, you're adding scalar fields to the theory. And when you add a field, you add a particle. And so the axion is one of the particles we added by adding those additional scalar fields, and it's got an axial coupling to quarks.
Yes.
Well, I'm out of the field, so I missed the experiment in order to detect the axions.
Yes.
We're talking about some resonances that were just in a certain
So
degree.
there's a
But I did actually I missed what the
okay. So the axion naturally decays to 2 photons with a tiny, tiny, tiny rate. So you'll never detect it just by trying to look for 2 photons coming from a dark matter axion decay. But you can stimulate that decay by having a very strong electromagnetic field. So you build a cavity. In the cavity, you put a very high magnetic field. Right? So it's a cavity. A magnetic field is, of course, an electromagnetic field. So you have a cavity with a very intense magnetic field. Now the process is the axion goes through the high magnetic field and converts into a photon. And in the process deposits a little energy in that cavity, which can be read out with a squid. And that sounds simple, but actually building the cavities, making them high enough Q, making them low enough temperature that there's not a whole lot of noise that's masking that tiny signal, and having sensitive enough squids to be able to read out, that's the work that's taken 30 years.
Thank you.
Second question I have, there are some experiments of light through a wall in order to detect not only axions, but axion light
And
particles
it's
in
the
general.
same kind of thing, right? So if an axion couples to two photons, then you have matter. Inside matter, you have strong electric fields. So as a photon goes through matter, occasionally interacting with the electric field inside an atom, it can produce an axion. So you can have that kind of effect, and then it can convert back again, and you can look for that effect as an experiment. Such experiments are not sensitive to the scalar parameters that would be the ones that describe dark matter. But there's no reason why you shouldn't search for axions in other parameter regions, and that's one of the ways you do it.
More questions?
Maybe I missed it in the talk, but how do you constrain the mass of your actions?
Well, as I said, they're another Higgs field, and there's another vacuum. When the Higgs field we know and love is some linear combination of those two doublets, and it has the vacuum value, which does the usual things that the Higgs mass does, gives us the mass of all the particles. But the other doublet field also gets a vacuum expectation value, and the scale of that vacuum expectation value, together with the coupling of axions to photons, those parameters together define the axion mass. In similar way to the fact that the pion mass is related to F pi, the axion mass is related to F axion. So there's few additional parameters in these theories. The reason the one doublet theory could be ruled out is there was really only one additional parameter in the theory, and the mass of the axion I predicted is ruled out experimentally, right? But with two doublets, or even just one doublet and one singlet, you've got enough parameters to evade those restrictions and get axion masses and couplings in the range that are interesting for dark matter. But there's a relation. For example, you can't let F axion be too big, or you overclose the universe with the axion, with the field that makes, the field that would be the dark matter with the right range of parameters turns out to be a mass density in the universe which is too great and stops expansion, right, and causes collapse. So that we can't have. So there's a limited set of additional parameters that you get in the theory by adding these additional Higgs multiplets. And they together give you the mass density of that field, they give you the axion-photon coupling, and they give you the axion mass. But there's a range of axion masses related to a range of couplings. Right? And that's why, let's go back to that picture, right? This range is the coupling, and this range is the mass. And the graph has been drawn, so the variable here is one that you get this allowed band.
Sorry. What about the rest of the standard model? This action can be coupled to the leptons, or?
Well, it's because of the Peccei-Quinn symmetry. Let's just do the simple two-doublet model. What you have to do to make the Peccei-Quinn symmetry in the standard model is the up quarks get their mass from one of the doublets, and the down quarks get their mass from the other of the doublets. And the combination of the vacuum values gives you the right, the vacuum value for that gives the right masses. So the additional symmetry allows you to say this Higgs field can only couple to the up quarks, and that Higgs field can only couple to the down quarks. Right, that's what the symmetry does for you. So in the standard model, there's not a lot of extra degrees of freedom by adding that extra doublet with the extra symmetry. And there's really, everything else looks pretty much like the standard model. I added another Higgs doublet. That means I added some charged Higgs particles. They're heavy. We can make them really quite heavy, so they don't mess up any experimental constraints that we have today. But the rest of the standard model looks completely unchanged.
Some further questions? Yes.
In your motivation, they were mentioned the matter and the matter asymmetry and the role of CP violation to get that. And since we know that the CP violation coming from the weak sector is very small, as you mentioned, we would expect to have some extra sources of CP violation.
Absolutely.
Where we should look for, or what would be, should we expect some dynamics from the actions in the early universe that would be the remnant of that? Or something like that, some direction? That
So I'm interpreting the question. CP violation tells us something about the universe, right? We live in a universe where there's lots of matter and very little antimatter. And that's actually a big puzzle, right? How did we get to be in a universe with lots of matter and very little antimatter? And as it said, the CP violation we know about actually isn't big enough to answer the puzzle. What's the puzzle? Well, again, if we take standard theories of cosmology, the universe went through a period of inflation and then reheated. The reheating is dominated by strong interaction processes and produces equal amounts of matter and antimatter. If you have equal amounts of antimatter, as the universe expands and cools, matter meets antimatter, annihilates and gives you radiation. And pretty soon there's nothing left. And we could not be here. So there has to be a difference in the amount of matter and the amount of antimatter produced at some time in the history of the universe. And Sakharov in 1967 told us that to produce that you need baryon number violation, obviously, because you're going to change the balance between matter and antimatter. You need CP violation, and you need to be out of thermal equilibrium, because thermal equilibrium would give you equal populations of equal mass particles. So when and how did the matter and antimatter in the universe get out of balance? Can we explain that with the CP violation that we know and love in the quark-weak interactions? And the answer is no. It gives us far too little matter left over. If we did the calculation, the best calculation we can do about how that could cause matter-antimatter imbalance, yes, it gives you an imbalance, but not enough to explain the matter density of the universe. So we know there's some other CP violation, possibly in the neutrino sector, possibly just add additional Higgses with CP violating couplings, and we don't know which of those answers explains the matter-antimatter imbalance in the universe. Either of them could. Unfortunately, both of them give, in order to make the story work, give you additional things, but at scales we can't probe very easily today, and maybe never will be able to probe. So it's a puzzle that remains an open question. But yes, there definitely, the CP violation we know in the quarks is not enough to explain the matter-antimatter imbalance of the universe. Yes, my husband says I should mention my book. I have to do a sales pitch, right? for those who want to read a non-technical book on this, it's called The Mystery of the Missing Antimatter, and I wrote it together with Yossi Nir, and it's both about the cosmology and the particle physics for a reader who doesn't want to read all the technical details. So.
More questions? Well, I have a final question. Sorry, just the last one. You were mentioning at the beginning something about CPT conservation as a symmetry of nature, but there are...
Well, it's a symmetry of any field theory that has, as I said, local Lorentz invariant Hermitian Lagrangian. And we all know and love that we want in a field theory a local Lorentz invariant Hermitian Lagrangian to get properties that we really want the theory to give us. So in field theory, CPT is a consequence of the theory. When you go to string theory, you can write theories that violate CPT. Experimentally, we have no evidence either way. But if we were to see a violation of CPT, it certainly would mean we need to build a theory that goes beyond field theory.
Yeah, just one thing, there are people actually claiming that they could find different ways, even in field theory, to violate CPT. And my question is whether this could change anything of your discussions,
Not in this story, no.
etc.
I mean, the current limits on CPT violation put it at a scale that really wouldn't change this part of the story, I believe. I mean, it's always dangerous to say theorists can't, because then some theorist will figure out some complicated way to do it. But as I think about it, it's very unlikely that you could write a theory that has an allowable scale CPT violation that messes up this story.
More questions? Yes.
Could you have more than one type of axions, so that come from different U1s, for instance?
Yes, well, different U1, you possibly could do that. I mean, you get these theories that survive, the ones that go behind us, have at least one additional Higgs singlet, which means they have one additional pseudoscalar particle. But generally, that additional particle is heavy. Keeping two of them light by having two symmetries, you could do, but I don't know why you would want to.
So I don't see any further questions, and I forgot the fourth one, so I won't pose it now. But let's thank again Helen Quinn, please.
Just to comment that there are going to be 2 other talks by Professor Quinn. This is next
Thursday.
Yeah, at 1. And
Jueves.
and Jueves, yes. That's going to be more general talk. Is that correct?
That is a little less technical than this
Less
one, but not much less technical.
Okay. You're invited. And there
After
is
all, Dirac equation is something you have to, I am not going to teach you the Dirac equation if you don't know the Dirac equation.
Okay.
But I will talk about the influence of that equation on the history of physics.
And there is going to be one in the Faculty of Science on Monday at 1 also
About education.
Education, yes. And you are all invited. Thank you very much.
Thank you.